Welcome to section 6.3. We're dealing with vectors in a coordinate plane today. This is a very physics directed lesson. So those of you that have taken physics before, this may seem much easier because of your physics background. So what we're going to do is talk about all these definitions first, and then we'll go into some basic information. What we want to start with is the idea of a vector. And a vector is a quantity that has both a magnitude and a direction. Okay, and we'll explain both of those in just a minute, but we denote a vector with a V. Okay, magnitude is the length of a vector, so it's how long this vector is. And we denote magnitude with like a double absolute value is kind of what it looks like. So double bar and the vector name V is in the middle. A unit vector has a magnitude or a length of 1. And we're going to show you how to find a unit vector today. Vectors can be represented with a directed line segment. There's an initial point P. Okay. And a terminal point Q. And so it's the idea like we did initial side and terminal side of an angle. And you're going to see it denoted two ways. We're going to write it either P and Q with a directed angle vector, or again, you're going to see it just as a V. And let me show you again what that looks like. It's saying we start at an initial point P, and we go to this terminal point Q, and we put an arrow because it's going towards the terminal side, and so that's what a vector PQ looks like. We're a lot of times going to put our vector in what we call standard position, and standard position means that you start with your initial point at the origin, and we do that most often in order to find the direction or the angle that this vector is going, because it's easier to work when your base point is at 0, 0. A vector can be broken down into its x and y components. That means its movement on the x-axis and its movement in the y direction. We call this component form, and so we're talking about the x and y components. And as you write component form, we say this is V1, comma V2, and then we use these like less than, greater than signs, and that just denotes component form of our vector. And so this is kind of the basic information, and what we're going to show you in this intro is how a vector works, how we find magnitude, and how we do all of the stuff that we've talked about so far. So I'm going to move this down, and actually I'm going to go like this. Okay, we're going to go right in the middle here. A vector V has an initial point at 1, 3. So 1, 3, that's my initial point, and a terminal point at 5, 6. So that's here, and we draw a vector pointing towards the terminal side. Okay, so we first drew our vector. 2, what is the magnitude? Again, another word for the magnitude is the length. And so as we find the length, what we're going to use is the distance formula, since they gave us 2 points. Call this x1, y1, x2, y2 if you want. It doesn't necessarily matter. But as we look at this, the distance formula says take the square root of the difference in the x's and square it, plus the difference in the y's and square it. So 5 minus 1 is 4, so we have the square root of 4 squared plus 6 minus 3 is 3 squared. Let me go this way. We have 16 plus 9, which is the square root of 25. So my magnitude in this for this vector is 5. Don't forget our magnitude is denoted with the double bar. I'm just going to write that in so we practice our notation. But again, in order to find the magnitude, what we're going to do is use the distance formula. Now I'm going to change my color because they're going to ask me now to move it into standard position, which means I take this initial side and I'm going to move it down to the origin. And to do that, I moved it down 3 and left 1. So I'm going to take my terminal side and move that down 3 and left 1. And so this is my vector V in standard form. And all you've done is just shifted it down. The reason we do this in standard form is because we want to write it both in component form and look at the angle or the direction that my vector is going. In order to write it in component form, they're asking you to go from the initial side, how many x's do you have to move? Well, it's like counting for slope. Basically, I move over 1, 2, 3, 4. So I move 4 in the x direction. So this is 4. And how much do I move in the y direction? 1, 2, 3. So 4, 3 in component form. To make the angle in number 5, we're asking what is this angle down here? Call it theta. Well, guess what? This makes a right triangle, so I'm going to use my right triangle trig. If I know the opposite side and the adjacent side, I'm asking what is the tangent for the sides 3/4. And the only way to find an angle is to take the inverse tangent of 3/4. And so I stick this in my calculator. Please make sure you're in degree mode so that we get a degree answer. And if we round to the nearest tenth, we get about 36.9 degrees. Okay, and so the angle that that vector makes with the x-axis is about 36.9 degrees. And so we wanted to show you at least how to write component form. And again, component form is just how do you move right or left, and then how do you move up and down to get from initial to terminal side. How do you find an angle? And most often we're going to use tangent because that's the easiest. And then how do you find the magnitude? And that's by using the distance formula. Okay, so that's the first intro that kind of gives you the basics. What we're going to work on is scalar multiplication now. So I'm going to slide this down. I'm going to start first with multiplying a vector by a scalar, and a scalar is just a number, okay? And here's what's going to happen. Absolutely the distance or the magnitude will change, okay? So the length of my vector will change if I multiply my vector by a number. But sometimes the direction changes, and it really depends on what k is, and so we're going to talk about that. The magnitude is a distance, and distance can never be negative. And so when we do this by a scalar, my distance is going to be multiplied by the absolute value of k. And if I were you, I'd make a note again. Distance cannot be negative. Okay, and that's why we're multiplying by the absolute value. The second one, or the third one, says direction stays the same, okay? So I'll be going in the same general direction if the k value is positive. So if it's positive, I basically follow along the same path. It'll go in the opposite direction if k is negative then. And we're going to show you both. So I want to first start by giving you a vector v, which is 3, 4. This is in component form. If it's in component form, then we're going to start at the origin for my initial side, and 3, 4 will get me to my terminal side. So I'm starting at the origin, and I go over 1, 2, 3, up 1, 2, 3, 4. Okay, and I draw to my terminal. This is my vector v. So if it's in component form, they are assuming that you start then at the origin. All right, let's talk about the magnitude. Well, if I go over 3 and up 4, you'll notice it's a right triangle. If I wanted, I could just say, let me use Pythagorean theorem and say, okay, 9 plus 16 is 25. And you'll notice this is what's above, so my magnitude is 5. And again, you can always make a right triangle. That's exactly what the distance formula is. It's just assuming that it's not at the origin. If it's at the origin, I just use Pythagorean theorem. Okay? And so what they want to do is say, okay, if this is what happens when you just do v, let's talk about what happens if I multiply things by a scalar. And so here's what I'm going to do. I'm going to take 2v and I'm going to do it in component form. And what ends up happening is I take 2 times the first number and 2 times the second number in my component form. Therefore, my points are 6, 8. So if I go on this and I go starting at the origin, this time I go over 1, 2, 3, 4, 5, 6 and up to 8. This is 2v. And you'll notice that this distance is double the distance. Okay, so the distance of the first, v, and you look at 2v, it's double the distance. Now I'm going to change my color a second. And I want to do -1/2 v. Okay, same thing. Take -1/2 times 3 and -1/2 times 4. And you end up getting, and I'm okay with decimal or fraction form here, but -1.5 and then -2. Now my graph's not quite ready for this, so let me modify this. Something like this. As I look at it, okay, let's look at my components. -1.5 down to, here is my -1/2 v. Now as I look, the negative has talked about changing its direction, and the 1/2, you'll notice this is 1/2 the distance of my normal v. So the negative changes its direction to the opposite side, and the 1/2 shrinks its length to 1/2 of the original v. Okay, and this is working in component form. This is graphically showing us the representation. So flip to the back, we're going to do some addition now. I'm going to move this up so I can see this. All of this. We're going to be doing vector addition. And algebraically or in component form, it's really easy. Graphically, it's a little bit more difficult. We call that geometrically, but I'll show you how it works. When you're adding two vectors algebraically, so when you're doing it in component form, you just add the x components and then add the y components, and you'll get your resultant vector. When you do it geometrically, and this is the hard part, you put the initial point of the second vector at the terminal point of the first vector. So what it says is where you ended your first vector, you start your second vector. Your final answer is called the resultant vector. Okay, so let's start with what we can. I'm going to start with W, and I'm going to put these, each part that I do, I'm going to kind of make a different color so you can kind of see. So if you have a couple of colors of pencils or crayons or something, grab those now. W goes from 1, 4 to 2, 6. Okay, so this is my W vector. And V goes from 5, 6, so 5, 6 to 7, 3. Okay, 5, 6, 2, 7, 3, so it ends there. This is my V. Okay. Now, to add these two algebraically, I want to have component form. And so when I talk about component form, let's actually write these out. W is, to get from my initial, I move right 1 and up 2, so 1, 2. To get my V, I start at my initial, and I have to go right 2 and down 3, so positive 2, negative 3. Okay, and again, be careful because you always start from your initial and go to your terminal. Okay, so algebraically we add them together. So W plus V, we're going to add our x's, so 1 plus 2, add our y's, 2 plus negative 3, and my resultant vector is 3, negative 1. Now, the problem is geometrically we have to show this. So I'm going to change my color, and I want this geometrically to be in red, so as you look at this. Now, here's what it says. I start with W, and I put V at the end of W. So I'm going to say I start W, and here's where I ended in W. The problem is I want to start this V, I want it to come over here. So if I start here, I'm going to basically move with my component form. Go down 2, or over 2 and down 3. And this is my moved V. Let me make sure that looks like a V. Okay, and so all I did is you want to, again, start your second one where the first one ends. Now this here is going to be my W plus V. And I'm going to end at the place where I ended. So I started here and I ended here. And the idea is, what is this shortest distance? It's like the idea of Pythagorean theorem. Instead of walking around the block, why not just walk straight there? That's the idea. So this W plus V, the question is, how did I get from the start to the end? Well, I went over 1, 2, 3 and down 1. So this is my resultant vector. Okay, and we're trying to show you geometrically what does it look like. And the idea, again, that I want you to get in your mind is, instead of walking around these vectors, why not just start at W and end at the end of V? Okay, let me change my color again. We want to take V minus, or W minus V algebraically. Here's the thing, we have to add a negative V. Okay, there is no subtraction of vectors. Instead, you can add the opposite. And so as I go through, I want to talk about what is the opposite of negative V. And I'm going to just stick this over here. So negative V is the vector, and I take the negative, so negative 2 and a positive 3. Okay, so I just want to keep that in mind. So W plus a negative V is 1 plus negative 2 and 2 plus 3. So 1 and negative 2 is negative 1, up 5 is what it's saying. Okay, now again, our goal is to show that algebraically that's the same, or geometrically that's the same, because here we went over 3 and down 1. So over 3 and down 1, that was this vector, right? So we showed it geometrically, and we're doing the same thing here. So I'm going to change my color one more time, and we're going to do W minus V geometrically. Now, we said you had to add the negative. Okay, so where W ends, so I'm looking at this one, where W ends here, I need to do the opposite of V. And the opposite of V said go, if I look over here, said go left 2 and up 1, 2, 3. So this here is my negative V. So again, the idea is, instead of starting at W and walking around these vectors, let's just walk directly to the ending point. So that means this, sorry for the not so straight line, is W plus negative V. Well, how did I get there? I moved left 1 and up 1, 2, 3, 4, 5, which is exactly what this says. Okay, so again, you're looking for, the idea is, and what you really have to keep in mind is you have to start the second vector where you ended the first vector. Okay, and that's one of the harder parts I think about today. Let's keep moving. We have this idea of a unit vector. A unit vector is a vector with magnitude or length of 1. Okay, we have this idea of putting unit vectors in terms of these i's and j's. And I is the vector that just has an x component, so it's the vector 1, 0. And j only has the y component, so it's the vector 0, 1. And basically what we can do is write all vectors in terms of i's and j. And we're going to show you that as we go through. Keep in mind, i's the x's, j's the y. Okay, so here we go. We're going to graph the I and the j. And if I always start at the origin, I is this one. And if I go to this unit 1, j is the one going up. Okay, so there's I and j. The second thing they want us to do is let v be a vector from 2, negative 5, to 7, 3. Okay, so here's my vector v. First things first, what is component form of v? That means, how did I move left, right, or up and down? So I start at my initial, I move right 1, 2, 3, 4, 5, and up 1, 2, 3, 4, 5, 6, 7, 8. So my component form is 5, 8. Okay, now we're going to graph this component form. All right, and as I graph this component form, I'm going to change my color so you see my movement. Let's go like this. So we start at the origin and we go over 1, 2, 3, 4. Let me just do it this way. Start at the initial, move it up 1, 2, 3, 4, 5, and over 2. So I take my terminal and I move it up 1, 2, 3, 4, 5, and over 2. And so this is my vector v in standard form. We want to write it in terms of I and j. So that means how many i's do I have to go to the right? Well, I go 1i, 2i, 3i, 4i, 5i, plus how many j's did I have to go up? Well, I had to start here and I went up 1j, 2j, 3j, 4j, 5j, 6j, 7j, 8j. And so what you'll notice is, how does that relate to component form? Well, really, these two are saying the same thing. They're just in a slightly different look. One with multiples of I and j, one in component form where it's just basically counting the number of spaces you go over. All right, so let's look at angles again. What angle does it make with the x-axis? Well, what we're going to do is kind of draw in our right triangle, where we said you go over 5 and up 8. So how do you find the angle? If I'm finding this inner angle theta, I'm going to use the tangent, because the tangent is opposite over adjacent. And if the tangent is, let me write mine correctly a second, if the tangent is 8 over 5, how do you find theta? Well, theta is the inverse tangent of 8 over 5. Therefore, theta is approximately, let's go to the nearest degree, 58 degrees. Okay, so the angle that it makes with the x-axis is about 58 degrees. Now, the last part says a unit vector. And right now, we don't know the length or the magnitude of this vector v. So we have to start by finding the magnitude. And the magnitude of v, because I've put v in standard form, is really Pythagorean theorem. Find the hypotenuse. So 5 squared, it's the square root of 5 squared plus 8 squared, which is the square root of 25 and 64, makes 89. And I'm going to approximate this a second. No, you know what? I'm going to leave it here for a moment. Okay, so we're going to leave it as the square root of 89. And I'm going to show you two ways to write this unit vector in exact form and in decimal form. So if I know my original magnitude is the square root of 89, if I want a unit vector, then what I'm going to do is I'm going to basically divide each component by the magnitude. So 1 over the magnitude, we don't necessarily like to divide quantities in a vector, so we multiply by the reciprocal. So as I look at this, I'm going to say 1 over the square root of 89 times 5. Let's do it this way. And 1 over the square root of 89 times 8. And if I asked you to rationalize this denominator, you would end up finding that you get 5 square roots of 89 over 89 and 8 square roots of 89 over 89. Okay, so that's in exact form where you rationalize the denominator. If I asked it to you in decimal form, you could actually plug this in your calculator and you'd get approximately 0.53 and 0.85. Now, if I wanted to check whether or not this was a unit vector, which means the hypotenuse of my triangle is 1, I could check by saying 0.53 squared plus 0.85 squared. Do you get 1 squared, basically, is the question. Does this make it a unit vector? And obviously we round to decimal, but if it's really close to 1, then you know for sure this is your unit vector. But there are 2 ways to write the unit vector, whether it's an exact form or a decimal form. Most of the time we're going to do exact form, but every once in a while a decimal is okay. So this is the idea of vectors. For us that haven't had physics, this is a brand new idea. For those of us that have had physics, this should be pretty much a review section for you guys. But please start on the homework, get looking at it so that you can ask some good questions once we're in class.